My name is Professor Duke Orata, and we have been having a series of these lectures. This is lecture 6, and we look at isobaric coefficient of thermal expansion. And it's denoted as alpha. It's a very important coefficient in engineering and sciences. We start by remembering that U as a function of volume and temperature. As you have said, U is internal energy, V is volume, T is temperature. And U being a state of function, we can write it as du is equals to del U, del V, dV, T constant, plus del U, del T, V constant, dt. And so if we divide this coefficient, throughout by dt, so that we want to obtain, we are interested in obtaining the coefficient del U, del T, and the constant pressure, that's the coefficient we are interested in determining. So we start from the very first principles where U is a function of volume and temperature. We write the exact differential for that, so that when we want to get this coefficient del U del T P constant, we divide throughout by dt, so that you have du over dt is equals to del U del V T constant dV plus del U del T, that is divided by dt, del U del T V constant dt divided by dt. And of course, dt divided by dt is just 1, or unity. And so we are left with del U del V T constant, which we have already determined from Joule's experiment. And we have dV dt, du dt, and the dt by dt has cancelled out, so we have unity. And so to now constrain this system to constant pressure, so that we change from total derivative d to partial derivative del. We're changing from d to del, that we said is d to del, and partial derivative means that you keep one or more variables constant as you vary the other. So we are constraining the system to constant pressure, so the d's will become del. So now we have del U, now del U del T P constant is equals to del U del V T dV. We have del U now also, this now del U del V over del T P constant plus del U del T P constant. Of course, remember that del U del T, this is simply heat capacity, CV, isobaric heat capacity. So let's look at the new expressions which have emerged after we've carried out the operation to get del U del T of P. So now what we have is that del U del T of P, which is what we wanted, is simply a CV plus del U del V T plus del V del T P constant. Remember that we had gotten this from Joule's experiment in the earlier lectures. And so we have left with del V del T of P. This coefficient here, del V del T of P, is the isobaric coefficient of thermal expansion, which is defined as alpha is equals to 1 over V del T of P. So this alpha is the isobaric coefficient of thermal expansion. Coefficient of thermal expansion. It's a very important quantity in engineering and sciences, and different materials have different alpha values. So from that, we are able to compute, for example, volume or temperature under constant pressure conditions. And we read this alpha as alpha is del V del T, P constant per unit volume. I repeat, alpha is read as del V del T, P constant per unit volume, or change in volume with temperature under constant pressure per unit volume. And like I said, you can calculate volume and temperature for various quantities if you have their alpha values. It becomes very, very important. For example, if you look at it, alpha V, it can be written as dV over dt. If you cross out this, cross multiply, you have alpha dt is equals to dV over V. So that you have alpha dt is equal to dV over V. And of course, you can carry out a calculus on, you can apply calculus to obtain values from this. If you integrate, then you can see that you get values which you can plug in the values of volume or temperature and be able to, using value of alpha, you can calculate value of volume or temperature depending on what you want to solve. Let us now look at another case where we want to obtain this coefficient, which we call the isothermal compressibility, Kappa. Thermal compressibility, denoted as Kappa. Once again, this particular case now will not use the expression for internal energy, we'll use the expression for enthalpy, and we assume that enthalpy is a function of temperature and pressure. We have already talked about enthalpy. Enthalpy, remember, is U plus pressure, the product of pressure and volume, that is U plus PV. So, being an exactitude, a thermodynamic state function is an exact differential, so we can write the total derivative as dH is equals to del H, del T, dt, P constant, plus del H, del P, dP, del H, del P, T constant. Because it's an exact differential. Enthalpy is an exact differential, internal energy is an exact differential, Gibbs free energy is an exact differential, and so forth. So we have dH is equals to del H del T of P, dt del H del P, constant temperature. Now, we know that is Cp, that is the heat capacity under constant pressure conditions. So, if we want to obtain the coefficient del H, del T, V constant, then we can again repeat the same process like we did with the case of internal energy by simply dividing the expression by dt. If we divide by dt, we get dH by dt is being equal to Cp dt by dt plus del H del P T constant dP dt. Again, that dt by dt is unity or 1. So we are left with dH by dt is equal to Cp plus del H del P of T del dP dt. So if we constrain the system now to constant volume, then we now have that the total derivative becomes a partial derivative, like we have already mentioned, so that becomes Cp plus del H del P T, and now del P del T volume constant. Now, we have two coefficients which we deal with, del H, del P, T constant, and del P, del T, V constant. So let's start by looking at del P, del T. And it will be from the other coefficient, del H, del P, that will be the basis of the next lecture. That will be the Joule-Thomson experiment. So let's look at del P del T. Now, to look at del P del T at a constant volume, we need to do a few operations here involving partial derivatives. One, we will use the identity which we refer as the permuter, and the permuter, if you have an expression del x, del y, del x, z constant, it permutes the thing, the coefficient, so that you have del y, del z, x constant, del z, del x, y constant. So if you look at that expression, it's a cyclic expression. You can see that if you cancel the del z's in your mind, then you will have almost the same expression as you had del y, del x, y constant. You have del y, del x. That's one way of remembering it. That if you cancel this quietly in your mind, then you will have what you started with. And the other identity which we'll use is the inverter, where if you have del y, del x, z constant, it is inverted, it becomes del x, del y, z constant. These are two important mathematical operators for you which are used in breaking down partial derivatives so that you get meaningful quantities from those partial derivatives. For those partial derivatives are not just abstract things, they're actual things, give quantities. You have already seen the value of alpha, and alpha is a very important coefficient, very, very important in science and engineering. So you need to know those mathematical identities to be able to break down some of these partial derivatives, as you're going to do now on this coefficient del P del T. So let's subject del P del T to the inverter first. Del P del T be constant to the inverter. So we are going to have minus del P del V del V del T. Of course, we are having here T constant, and here we are having P constant. We're having T constant, and we're having P constant. Now, if you look at it, this coefficient here, del V, del T of P, is alpha V, which we have seen in the earlier derivations. So that what we now have here is alpha V minus alpha V del P del V of T. And so if you use the inverter on that other coefficient del P del V of T, we will have minus alpha V over del V del P T constant. Now this coefficient del V del P T constant is kappa, which is isothermal compressibility. Isothermal compressibility. And so we define it as kappa is equals to minus 1 over V del P T constant. I repeat, that is isothermal compressibility. Another important quantity in engineering and sciences, isothermal compressibility. Very important quantity in engineering and sciences. And so again, this is said as change in V with respect to P holding temperature constant per unit volume. That is how we read out this expression for kappa. And this kappa is a very important quantity. Now you might be wondering, why is there a negative sign? Why do you have that negative sign there? Why do you have that negative sign there? That is because if you look at the quantities in the coefficient, we have volume and pressure. And volume and pressure are inversely related by Boyle's law. So the negative sign takes care of that aspect. So the negative sign takes care of the element of Boyle's law. Boyle's law, where pressure is inversely proportional to volume. In other words, as you increase the pressure, the volume decreases, and as you decrease the pressure, the volume increases. So it takes care of that inverse proportionality between pressure and volume.